Hereby I open this academic ceremony in which Margaux Frigoli will defend the academic thesis Fighting Bacterial Infections and Antibiotic Resistance with Molecularly Imprinted Polymer-based Sensors. May I invite you to present a summary of your study and the conclusions of your thesis?
Dear Prorector, thank you for the introduction. Dear opponents and supervisors, dear family, friends, and colleagues, welcome to my PhD presentation, where I'm glad to show you what I've been working on for the past 4 years. The topic of my research is titled Fighting Bacterial Infections and Antibiotic Resistance with Molecularly Imprinted Polymer-based Sensors. Before we dive into the results discussion, I would like to introduce the reason why this research was carried out. For this reason, we have to go through the understanding of bacterial infections. These infections are a well-known global health concern, and it's an issue related to many sectors, including food safety and healthcare. And the reason why it's such a big issue is that in 2019, more than 7.7 million deaths and many more infections were linked to bacterial pathogens. Pathogenic bacteria can belong to many categories, but now I'd like to focus on a notorious group whose acronym is ESCAPE. This group includes 6 pathogens that are particularly dangerous for human health and for the environment, especially because they can resist antibiotic treatments. In this slide, you can see an overview of the names of these 6 bacteria belonging to the ESCAPE group. They are divided into gram-positive and gram-negative bacteria based on specific features they have on their cell structure. Among the gram-negative ones, Pseudomonas aeruginosa stands out for its infectious properties. Therefore, it's important to find ways to quickly detect its presence and to prevent the infections to spread. In this slide, you can see what the bacterium looks like. It's an opportunistic bacterium found in soil, water, and vegetation, and it's particularly well known for its antibiotic resistance. Furthermore, one of the main challenges connected to this pathogen is that it's difficult to detect, because the methods used are time-consuming and expensive. Here, I would like to quickly show you an overview of the technologies that are currently used to detect the presence of Pseudomonas aeruginosa or bacteria in general. Among these, we can find the so-called gold standard technologies, such as HPLC, GCMS, that are very reliable but also expensive. On the other hand, we also have culture-based methods, which involves the growth of bacteria in a lab environment, which, as you can imagine, takes quite a lot of time and also requires qualified personnel. Other sensing technologies are, for instance, ADB-based sensors, PCR, or ELISA, which are also solid technologies, but have the common drawbacks of having high prices, being non-portable, or being too time-consuming. With this in mind, it's clear now why my research started with the aim of finding a versatile technology to detect bacteria in a fast and low-cost way. The technology that I'm talking about is called biosensors. Here you can see an overview of the working principles of biosensors. On the left, you can see the target of interest, for instance, a dangerous bacterium that meets the sensor surface, the so-called biorecognition element here in yellow, very visible, and thanks to a transducer, it generates a response under the form of a signal. A specific type of biorecognition element, so the yellow part that you have just seen, are the so-called molecularly imprinted polymers, or MIPs for simplicity. These materials are polymer-based materials prepared in the lab with specific polymerization techniques, and they are used to create polymeric matrix with cavities that resemble the shape and interactions of the target molecule. In general, MIPs are made using specific materials, which you can see here, monomer, cross-linker, and others, which have to be chosen depending on the target or on the application. In addition, every MIP has a negative control material, namely the same exact polymeric matrix, but without the cavities that are responsible for the target recognition. These materials are called non-imprinted polymers, or NIPs, and they're used as a reference material to better understand the MIP's performances. And here you can see the whole sensor in action. Once that the target gets detected by the sensor, the transducer converts the signal into something that we can see or quantify. Specifically, during my PhD, I focused on 2 different readout technologies, the thermal and electrochemical readouts. I hope this introduction gave a bit of context, because now we're going to dive a bit into the results. In this slide, you can see the overview of my first project that focused on the detection of Pseudomonas aeruginosa in an original way. So in particular, instead of detecting the whole bacterium, I focused on the detection of pyocyanin, one of the main toxins secreted by the bacterium. The molecule was synthesized in the lab, and you can see its molecular structure here. The MIPS were prepared to specifically detect pyocyanin, and after that, the MIP particles were immobilized onto a conductive aluminum layer to perform thermal analysis with the so-called heat transfer method. This method belongs to the thermal readout technologies, as I mentioned before, and the working principle involves a heat flow through the sensor. This heat flow gets stopped when the target binds to the sensor, therefore generating a signal under the form of a temperature decrease. So here you can see some key results, and let me guide you through the graphs. These are temperature signals of MIP, shown in black, and NIP, the negative control that I mentioned before, shown in red. It was observed that an increasing concentration of the toxin leads to an incremental temperature decrease, and this is caused by the binding event of pyocyanin onto the surface of the sensor. On the right, you can see the same results, but translated into a relative temperature change for clarity, where you can see even more the efficacy of the MIPS compared to the negative controls. Following the same type of curves, selectivity studies were performed to preliminary check if the sensor was able to differentiate between pyocyanin and other contaminants, namely compounds with similar structures or compounds that can be present in the sample analyzed. And in this case, it's difficult to read, but we tested the sensor toward glucose, vitamin C, phenazine, and riboflavin. The results were very good, showing that the sensor is able to selectively detect only the toxin, this blue line. Therefore, the last step of this project was a real-life study to check if the sensor is also able to detect the toxin in a more complex liquid, because before everything was done in a simple buffer solution. In this case, saliva was chosen for the study as a biological sample, and the results showed that the sensor can detect pyocyanin also in more complex liquids. Let's move on to the second project. The aim of this study is the same as the one before, namely indirectly detecting the presence of Pseudomonas. But instead of using a toxin, this time we use a quorum sensing molecule, which is a small compound that bacteria use to communicate among each other. Its name is here N-butyryl homoserine lactone, but more simply BHL. You can see structure here. This molecule was also prepared in the lab and was used for the preparation of MIPS. Subsequently, the MIPS were immobilized onto the surface of a screen-printed electrode, this that you see here, that can be used as a sensor with electrochemical readout. And in particular, the readout chosen is called electrochemical impedance spectroscopy. Again, here you can see an overview of some important results. In this graph, you can see the impedance dropped caused by the interaction of BHL with the MIPS surface. And here, once again, you see the same data, but translated into relative impedance change, which you can find on the y-axis, and the actual concentrations used on the x-axis, showing even more clearly that the MIP-based sensor works in a more effective way compared to the negative control shown in red. Once again, preliminary selectivity measurements were performed using as interference the molecules that you see here, and good results were obtained. Therefore, the last step was once again a real-life sample analysis, and in this case, tap water was chosen because of the large number of contaminations that are spread through tap water specifically, for instance, in hospitals or when water is used as irrigation. And the results obtained were good. In fact, it was observed a similar sensor response at increasing concentrations of BHL. Until now, we stressed the issue caused by pathogenic bacteria, but this problem is strictly related to the so-called antibiotic resistance, namely the ability that bacteria develop to resist antibiotic treatments. Antibiotic resistance is caused by misuse of antibiotics because many times they're used to prevent infections rather than to treat them, or they are not disposed correctly, and these and other reasons lead to their accumulations in animals and in food. For these reasons, specific regulations are followed to limit the amount of antibiotics in food samples. Nonetheless, the methods used to detect the presence of antibiotics present the drawbacks that I listed before. Therefore, a rapid way to detect them could make a big difference to fight antibiotic resistance and for food safety. This is why in this project we focus on the detection of streptomycin, which is a widely used antibiotic whose structure you can see here. In this project, we prepared a specific material to enhance the interaction of the MIP with the target. The MIPs were prepared this time via the so-called electropolymerization directly onto the surface of the electrode, which you can also see here. This is a picture showing the electrode in real life, and the readout chosen to generate the signal belongs again to the electrochemical readout technologies. You can see here some of the results, starting from how the sensor was prepared through the process called electropolymerization. The polymerization was performed over 5 cycles, which you can see in this graph. And here you can see the results of the sensor's response to increasing concentration of streptomycin. The results show that the black line of the MIP generates an increase in signal compared to the negative control, shown in red. And once again, selectivity was studied choosing these compounds for preliminary study, obtaining good results. Therefore, a preliminary real-life application was carried out using milk. And the results obtained were overall good and showed that this method can be potentially used for fast antibiotic detection even in food samples such as milk. And similarly to what I've just presented, this last experimental project also focused on the detection of antibiotic residues, and in this case, it focuses on sulfamethoxazole, a widely used antibiotic, especially used to treat livestock. The MIPs were also prepared in the lab, and once again, HDM was used as a thermal readout method. The results are shown here. You can see the signal increase of the red line of the MIP at increasing concentrations of sulfamethoxazole, while the black line of the negative control doesn't show a response to the target. And also for this project, selectivity and real-life analysis in milk were also performed, leading to positive results and concluding this way the experimental research that I carried out during my PhD. In conclusion, we can say that MIP-based biosensors showed promising results even at very low concentrations for both indirect bacterial detection and antibiotic detection, which are 2 strictly related problems. Nonetheless, further validations and research is needed to understand the durability, stability, but also the portability of the sensors and of the sensing devices. And a possible step for the future could be to study novel materials that could enhance the selectivity of the sensor and the sensor's performances overall, or to test these sensors in the presence of a wider variety of interference and complex samples. But for the moment, I thank you for your attention, and I'd like to thank everyone who's here today. Thank you very much for coming, and especially the sensor engineering group.
Thank you very much for this very clear presentation. And before we move over to the defense, let me first welcome the audience. Good to have you here, and also welcome to the audience that may be joining online. And let me also introduce the supervisory team, which you will find opposite of the table. Dr. Bart van Grinsven, Professor Thomas Klei, and Dr. Hanne Delian. They will not be asking any questions, but now at least you know why they're here and why they're sitting there. My name is Ralf Peters. I'll be guiding you through the ceremony as the pro-rector at this defense. And then it's time to move to the discussion part. The opposition will now be opened by Professor Kim Regaard. She was the chair of the assessment committee, and she holds a chair in circular plastic here at Maastricht University. Please, Professor Regaard.
Thank you, Mr. Pro-Rector. Dear candidates, my questions will be focusing on the polymer side of your work. I was very much triggered by the concept of these molecularly imprinted polymers. I did note that currently the description of the system is quite morphological. It's very focused on matching geometries of what they're supposed to sense. So I would like to have your opinion on how you would feel you can further tailor these sensors and their sensitivity by using other properties such as surface chemistries or mechanical properties and their response.
Highly esteemed opponent, thank you for your question. This is for sure interesting to dive in because the chemistry of the materials behind the MIPS, so the biomimetic part of the sensor, is very It can be tuned in many ways, let's say. What we do in general is trying to find specific functional groups that tend to interact with the target in specific ways. For instance, having non-covalent interactions such as acid-base interactions, hydrogen bondings, van der Waals forces, and similar. But indeed, these properties are not just related to the core of the polymer, because when you synthesize the polymer, you synthesize it in the presence of the target itself, which is key to arrange the geometry, as you mentioned before. But of course, the functionalities are also present on the surface. Mechanical properties that can be used to, let's say, enhance the sensitivity or in general the working principle of the sensors are also possible. Maybe it's also possible to use polymers that instead of being rigid are maybe more thermoplastic and can be used to detect the sensor, detect the target also in a wider variety of temperatures. But I'm not sure if this was tested or if this is possible. Of course, further research is always needed before saying everything. But the key of these molecular imprinted polymers, so the strong suit, let's say, is that they are also resistant to harsher conditions, such as temperature. So in general, it's good that the mechanical properties of the polymers are rigid and cannot be tuned too much, because that's what we want. That's what we hope, that the sensor doesn't change over time and it's resistant and can be stored easily and everything.
Okay, thank you. Somewhere in chapter 3, when you were investigating the binding to piocyanin, you showed a couple of binding isotherms for different MIP compositions. I was wondering how you think such binding would evolve if you also enter pressure into the equation. So if you don't just look at temperature, but pressure either of the system or of the interaction between the MIP and the bacteria.
So this is a very interesting question, because in general, the parameters that we take into consideration, of course, besides the concentration of the target, are pH. That's why the preliminary studies are always done in buffer solutions to control the pH and control the ionization form of the molecule. Under pressure, I personally think that it wouldn't make a big difference on the signal response, because that's also one of the key features of these materials, that they can be used with harsher conditions, as I mentioned before, so not only temperature but also pressure, which are also strictly related. We never tried in our lab and in our studies to measure these materials under harsher pressure conditions. We usually measure at atmospheric pressure, right? But it could be helpful to maybe investigate these for maybe obtaining a faster response. That maybe helps, but I didn't investigate this part specifically.
Okay, thank you. I would like to invite your paronyms to read out proposition number 2.
MIP-based biosensors can contribute transforming bacterial detection but require better scalability.
Thank you. Could you comment on the scalability, especially in the framework of the production of the sensors?
Yes. So among the methods that I use to synthesize MIPs, there are 3 main methods: the bulk polymerization, precipitation polymerization, and electropolymerization. These are not equally scalable, because the bulk polymerization and precipitation polymerization can be ideally scaled in an easy way, because what we do in the lab is using a small reactor, a small vial, to prepare these materials, but these ideally can be replicated into a higher, so you can easily scale it up by putting these materials into a bigger batch, which is for sure one of the next steps of this research, because scalability is required in case you want to sell a product or if you want to think about bringing any technology further. In the other hand, on the case of the electropolymerization, it might be a bit trickier. I think it's one of the, currently, I think it's one of the main limitations for electropolymerization and these types of polymers, because it's not as easy as I mentioned before. You don't simply need a bigger reactor, let's say, as in the case of precipitation and bulk polymerizations, but this is the issue that I addressed in my propositions.
And if we relate that to cost, of course, cost will go down with scaling, but how relevant is cost? Is this something which is permitted to be relatively expensive, or should it be cheap?
It must be cheap. Everything related to costs has to be cut if you think about selling anything. In this case, the advantage of the two types of polymerizations that I mentioned before, so precipitation and bulk, is that especially during my thesis, I used quite cheap materials, so a scale-up would potentially cut the costs because the smaller you work and the more expensive it is to access the materials. Whereas if you have to work on a kilogram base or tons, even better, it's possible. For the case of the electropolymerization, I think it's a bit trickier, as I've already mentioned, because the sensors themselves, so the electrodes that I use, that I also showed the picture before, they have a price. The prices can be cut in that case by maybe trying to produce them in-house or with other technologies, developing patents and stuff like this, but indeed the cost is something that would play in our favor during scaling up, in my opinion.
Okay, thank you. That's all for me, Mr. Prorector.
Thank you, Professor Regaert. Then the opposition will be continued by Dr. Gavin Phillips. He was a member of the assessment committee, and he's an associate professor at Maastricht University and as well as the director of studies of the bachelor program in circular engineering. Dr. Phillips.
Dear candidate, I'd like you to step back from your thesis a little bit, and maybe tell us a little bit about why you explained the context of the importance of infectious bacteria and the importance of the treatment of the infectious bacteria. Why did you choose the particular systems and chapter structure during your investigation?
Yes. Esteemed opponent, thank you very much for your question. This is a very broad question, and let me try to break down, talking about, first of all, bacterial infections, because as I mentioned, the thesis is split into these two big problems, which is antibiotic resistance and bacterial infections. In the case of bacterial infections, nowadays it's really spread, the issue created by bacterial pathogens, and many infections that are spread in many different ways. For instance, irrigation was one of the issues that contributed to the presence of bacteria also in food. There were multiple cases of bacterial infections due to vegetables, lettuce, something that you would never think ideally that could have bacterial contaminations. So not only meat, burgers, there are so many documentaries on this also on Netflix that I really, by the way, recommend to watch to also develop awareness on this topic. And the reason why I chose to act in this way, so to develop the thesis in this way, is that I wanted to prove that it's possible to detect bacteria also without using the bacterial cells to prepare the sensor, because that's also a problem related to the question that I've just had, so related to scalability, because if you have to use the bacterial cells to produce the sensor, you can imagine that it's not that handy. It's also dangerous, because if you have to use dangerous bacteria to develop a sensor that potentially prevents from the bacterial infection to spread, it's a bit counterintuitive, I would say. That's why I decided to indirectly detect the presence of bacteria, so to use toxins or quorum-sensing molecules, so these small molecules that the bacteria use to communicate among each other. so that it would be much easier, first of all, to scale up the process, but in general to also handle it in the lab, because handling small molecules is way easier than growing bacteria. And I also had experience on these thanks to a collaboration on my first project. It's really hard to grow bacteria. Besides, they grow everywhere, but when you try to grow them in the lab, then yeah, it's not that easy anymore. And to conclude the answer to this question, I would also like to add the part of the antibiotics, which, as I mentioned, is strictly related because, of course, their accumulation in animals, especially when antibiotics are given to livestock to prevent infections rather than to treat them, especially in intensive livestock cases. That's a problem because, of course, when you have your antibiotics in food, and there are many limitations to really limit the quantity of antibiotics that a food can have. For instance, milk is really regulated. Their accumulation in food can lead to further strengthen the bacterial defenses, let's say. So they get more used to the antibiotics, therefore more aggressive, therefore more difficult to treat.
Okay, thank you. And how do you feel about the balance between those two parts? So the bacterial detection for disease versus the antibiotic resistance. In your wonderful thesis here, there's a balance between the volume of work. What's your feeling about the importance proportionally of the two parts of the problem?
That's a very good question. I think that they really go together, and that's also why in my thesis I put them one on one side, so the antibiotic pills on the front and then the toxin on the back, because the issue that they generate is strictly related. I would say that antibiotic residues are potentially less harmful because, of course, we also use antibiotics to treat ourselves when we are sick or anything. So they are potentially not dangerous for human health, whereas, of course, bacterial infections and bacteria in general, they are. So I would say that bacterial detection has a higher priority if this is what you were asking, but I still have to underline and to say that they are very strictly related issues.
Okay. So I had a specific question about your chapters on detection of antibiotics in milk. They finish on you spike milk samples and you detect your analyte in a real milk sample. Did you do any work, or what do you think would be important to look at the actual detection of the analyte in a real system?
Yes. When we talk about milk, we talk about a very complex liquid because, of course, it's full of many other contaminants in this case because you want to detect the antibiotic, but it's also full of fats and, in general, also bigger molecules that tend to interfere a lot with the sensor's response. For this reason, in one of the two works that I had where I used milk as a real sample for antibiotic detection, so the first time I used streptomycin as a target, the second time sulfamethoxazole, they are both widely used antibiotics, but I wanted to try to test them with two different readout technologies. So in the first case, I use an electrochemical readout technology, and in that case, being so sensitive, the electrochemical readout, which is one of the big advantages of these readout technologies, you need pretreatments for milk samples, which means that you need to remove the fats, for instance, or these bigger molecules that we were talking about before to help the signal to not be affected by these contaminants. And in general, it's possible to work with more complex liquids, but every liquid, every sample has a different chemistry that needs to be studied in advance. That's also why in the conclusions I mentioned that it would be good to enhance the chemistry of these materials or to test them with more complex liquids.
Okay, so in a real system, so you've got a milk sample in the lab. How do you know your milk sample has got nothing in it already?
There are other tests, so other sensors that work in a different way compared to these that can be used to pre-screen the presence of contaminants and antibiotics in this case in the milk. You can also use analytical techniques that are solid, and we were lucky enough to have in our lab, such as HPLC, for instance, that LCMS, does give really immediate responses in that case. Another way to validate it, but with your own technology, so with the technology that I validated, that I used is to run the milk sample non-spiked and see if that actually gives a response. If that doesn't give a response, it means that the template, so that the target molecule is not present. Therefore, you can continue with your analysis. But in general, pre-screening is always recommended. And it's for sure also one of the future steps that might be done for some of these chapters.
So if you went out into the real world to, say, a dairy farm or a dairy process plant, would it be possible to get samples that someone, not yourself, already knew there was some contamination in them to see how the sensor system performed, where there might be other contaminants that might your method might be sensitive to?
This is really the key of all the sensors technologies in general, the cross-reactivity, right? Because you never know what's really present in a sample, and that's why further studies are always needed to be 100% sure, or let's say 99% sure, that this sensor can really differentiate between your target and other analytes. But indeed, yes, it's possible to use take a sample from production. These sensors were also developed to be used in a more portable scenario, let's say, so not just in production, but also in places where, chemistry labs are not really accessible. So you can just take a sample of your milk in this case, measure it, and see if it gives a response or not. So you can see if it has the contamination or it doesn't.
Okay. Thank you very much. That's
Thank
for
you.
me.
Thank you, Dr. Phillips. Then the opposition will be continued by Professor Gerard van Rooij. He was a member of the assessment committee, and he's also the secretary of today's degree committee. And he also chair in plasma chemistry here at Maastricht University. Professor van Rooij.
Thank you, Mr. Prorector. Geachte promovendus, dear candidate, congratulations, a sound thesis, far out of my comfort zone, at the same time very near to my interest, because normally I shave. We don't know each other, you see now a beard, and the reason is a bacterial infection. I just recovered thanks to antibiotics, so it's very dear to my heart, this work, but it also raises many questions. So let's start with propositions. I like it when propositions are being made, so then I always start with propositions. And in this case, proposition 6. May somebody read that out?
Early diagnosis is underestimated, but essential for better health outcomes.
If I read that, I'm triggered because I already tell my kids that it's important to go early to the dentist for an early diagnosis to limit the damage. So why do you say that early diagnosis is underestimated?
Hi, esteemed opponent. Thank you very much for your question and for your kind words. Early diagnosis is underestimated is for sure something that I might explain. And the reason for this is that sometimes it's easier in healthcare settings to, instead of, rather than having early diagnosis, curing and treating infections that are already ongoing. So in this case, in my thesis, I wanted to make clear that one of the best ways to prevent the infections to spread is to prevent them. So for this early diagnosis to take place, I mean taking samples, for instance, what we were also discussing before the samples are actually spread, before the samples are consumed or sold. Unfortunately, this is not always the case because early diagnosis is sometimes expensive, so it's not chosen many times because of this reason.
I get where you're going. We have to hurry up, sorry.
Okay, sorry.
So now I also see the picture why your sensors could help there. They should be cheap, fast, easy, everywhere. So then you come in the area of false positives, false negatives. Have you thought about that? Where is the weakness of your sensor? And is it then still a good sensor?
Okay. Interesting question. False positive, false negatives are for sure like the best friends and worst friends of sensors in general, because it's always something that you have to take into consideration, but this for every sensing technologies. In this case, of course, what I'm presenting here today is a feasibility study, so just to see if the science as we think of it can be applied to the sensors. But further validations, as I specified before, are needed for these sensors to be really solid. And one of these is for sure to try to test multiple samples, hundreds, thousands, and see how many false results you get. And this is the only way to have a solid answer to this.
Okay, I am a bit allergic for more research is needed. But okay, I let that one go.
More research is always needed.
No, definitely not. But let's go, because another one is, it should be cheap. Probably it should also be quantitative, not?
Yes.
And is it quantitative?
So for this thesis, the goal was to have a 1-0 type of response, so to understand if the infection is there or not to quantify the actual presence of contaminants.
Okay. Yes, I want to go more specific in the direction. For example, the figures that you showed in your presentation, 3.7, 4.8. Let's start with 3.7.
What page can I find that?
106.
Thank you.
So there I see, for example, starting at the y-axis, I see a small change in temperature.
Very small, yes.
Yes, very small.
It's a small molecule.
That's a link that I had not expected. A small molecule with a small temperature. But so I also see concentrations here.
Indeed, in the micromolar range.
With my glasses I thought it was even pico, but it is micro.
Sometimes we also reached other concentrations, but in this case it was very important to work in the micromolar range.
And is micro, is that a lot or not?
In the case of pyocyanin, so the toxin that we detected in this case, this toxin here, it was important to work in the micromolar range, which is definitely not a lot, but is still a lot in terms of sensing, because we can reach even way lower concentrations, picomolar range, as you mentioned before. But for the pyocyanin, that's the concentration range that is present in biological samples in saliva. So there are many literature results that show that pyocyanin is present in these concentration ranges. Therefore, ideally, the reason behind this research was to develop a sensor that can be used and put like as a swab, so that you can take a swab, you take a sample of saliva, therefore you can see if the infection is ongoing on a patient, right? On a biological.
But if I I caught this bacterium, how many micromole do I need to get in contact with in order to become sick?
So in general, the concentration range that determines that you have an infection ongoing can be from 0.1 to 10 micromolar, to give you a range, but it's my estimation. I hope this is an answer.
I was more afraid of getting ill than diagnosing that I'm ill.
They're both very dangerous indeed. So,
Hey, but let's go to the other axis, because there I see 10,000 seconds. Then I think that's not really fast, huh?
Yeah, I might agree on this. The point of this signal and this research is to build up, let's say, calibration curve to see how the sensor behaves to these specific concentrations of the analyte. And in order to do this, you want to see when the sensor tends to saturate. And on the page on your right, you can see better the same exact results, so done in the same way, thermal readout technology, but where you can also see the saturation. So the reason why we use such a long time, because in this case we're talking about 2.5 hours, if you convert the seconds into hours, is to really see how the sensor behaves at longer exposures. But if you...
And does it behave?
Behaves good.
Oh, good.
Yeah.
And if you now look at the error bars in the right graph, where do they relate to? Because I find them surprisingly small if I compare with the temporal variation in the left graph. Is that now a misjudgment of me, or have you averaged over hours to get to a small error bar? What did you do there?
I have to say, I don't remember exactly how this was done, but it's possible that I indeed averaged over the hours and the signals among themselves for these, to get these kind of error bars.
And if you, so I see this as an error bar from the measurements, and in the end, forecasting sensitivity towards a quantification, then we are talking not about stochastic variations, but about systematic errors. What would you think is the systematic error in this graph?
In which graph exactly?
For example, yeah, and we are looking at figure 3.7, so that's the right graph.
The systematic error.
Is that 5 on an axis of relative temperature difference of 1 degree? Or is that, I have no idea how I should feel that accuracy.
So I don't think that, like, in this case, any systematic error can be visible on this specific graph. Maybe an issue that can be related to these type of signals is the stability of the temperature in the environment, which could lead to indeed a systematic error. That's why it's important to also control the environment where the sensor is created, but this is harder to say than to do, let's say, because you work with a flow cell. You could put this flow cell into a climatized chamber, or in general control the temperature where this is performed, because of course in this case we are looking at temperature changes, so it's very important to not get contaminations from outside.
I have one small... are you a careful person?
In general, yes.
In general, yes, because I suddenly stumbled over the word carefully in your thesis.
I'm very careful.
Yeah, it's used only 6 times, so it's not so much worrying, but I'm very now curious. You talk about, for example, on page 92, on carefully chosen reagents. So what have you done then, if you have carefully chosen reagents?
In general, it's always good to be careful in life.
Yeah, no, they're very good, yes. I'm not doubting that.
But what I mean with the carefully chosen is also related to what I presented before, because the materials that you use to synthesize the molecular imprinted polymers have to be chosen based on the target and on the application. So that's why I meant that carefully is key. Not only the application is important, but also the prices, as we were discussing before. So we don't want great monomers that can enhance in a great way the sensitivity of your sensor, but then they cost a lot, because then there are other issues that have to be addressed. So that's why I mean that there are specific features that you have to carefully evaluate.
So you have done a rational choice.
I like to think so.
Yes. I also like to think so. With that, I think
Thank you very much.
I'm very pleased with the discussion. Thank you.
Thank you very much, Professor Van Rooij. Then the opposition will be continued by Professor Thorsten Wagner, was a member of the assessment committee. He holds a chair in optical micro and nanosystem technology at the Fachhochschule Aachen. Please, Professor Wagner.
Yeah, thank you. Thank you for the very nice presentation. I would like to continue with the careful part. So usually when you are at the level of your research, you prepare your sensors very carefully, but you also prepare your samples very carefully, your measurement samples. So how does the sample matrix, and particular the change of certain parameters, influence the heat transfer method, the accuracy of the heat transfer method? That would be something I would like to know.
Highly esteemed opponent, and thank you very much for your question. In this case, there are different parameters that we take into consideration when we have to shift from one sample to another. Let me just explain first that the preliminary studies that you see in every chapter are done in buffer solutions, so solutions that are able to set the pH within specific ranges. And this is strictly related to the choice of the real-life sample that I presented in every research, because usually if I study the preliminary reaction to the sensor in a buffer solution that has a pH of 7.4, for instance, or in a neutral range, let's call it, I try to use as a real-life sample something that has the same pH range. In this case, for instance, saliva, the buffer solution that was used in the beginning is PBS, so 7.4 pH. And saliva is also a natural buffer solution, also around this pH range. So that's why it was chosen. Milk, for the same reason, is also falling in this neutral pH range. And pH is one of the key parameters that always have to be carefully looked at because of course, changes in pH can influence a lot the signals generation, especially if we're talking about ionic interactions.
Mm-hmm. Okay, so pH. So your method would be to keep the pH level strictly constant.
Yes, and for the thermal, since you mentioned this specifically, also what I said before about the temperature.
Okay. So when it comes down to the heat transfer method and temperature, as you mentioned right now, because I'm a control engineering guy, I have to ask in this direction, so I'm sorry for that. But what do you think is the accuracy you could obtain from your measurement setup in terms of really the measurement electronics, the measurement device, the sensors? Do you see there's a lower limit where you say, because we mentioned already there's a very small deltas you are measuring.
Yes.
Is there a natural or a limit imposed by the device itself? You can't measure smaller than that. What would be that limit? Yeah.
Yes, in this case, you could potentially, because if you think about, for instance, a picomolar range, which is very small if you think about the concentration itself, it can be still enough to measure like a signal, in this case with the thermal readout. But the surface, so the conductive layer that you use has to be enhanced in certain ways. It has to be better in detecting this variation of temperature, better in conducting.
Okay, but is there a limitation in terms of sensors? Maybe the sensor is not able to see a change of a thousandth of a degree Celsius or something like that.
The question if it's there a sensor that can detect a huge temperature variation?
Whether it can, what is the smallest amount?
The smallest amount that you can, I think that in some cases in our lab and also with some of the people that are sitting here, the smallest variation that you can see is in the 0.05 degrees range, if I'm not mistaken.
No, it's okay. I just wanted to know whether you know a lower limit and you're not happily reporting a millionth of a degree or something like that.
No.
Okay, that's fine. Yeah, thanks. When it comes to the MIPS itself, also here the matrix should influence it. You mentioned it already, but maybe you can elaborate a little bit more. What are the effects which can happen to MIPS if you have changes in the measurement matrix, in the sample matrix?
Yes, if you have any variation in the sample matrix, so if you switch from a simple solution, such as a buffer solution, to a real-life sample, the functional groups that are responsible for the interaction of the polymeric matrix with the target also can have these, let's say, non-selective bindings. And that's why it's so important to use negative controls. In this case, the non-imprinted polymers that I mentioned also before in my presentation are key to see if your sensor is actually working, if your MIP-based sensor is actually working, because the polymeric matrix is made exactly in the same way, so using the same materials. So ideally, on the surface, you have the same functional groups, but you don't have the cavities. Those are also important for the interaction.
Okay. And then within your propositions, you mentioned number 3. Maybe someone is keen enough to read that.
High sensitivity in biosensors does not always translate to better performance.
Yeah, thank you. I was wondering, because not in your work, but also during your research in your introduction chapters, there's always a discussion of whole cell biosensors or whole cell MIPS devices which detects the entire bacteria. And I was wondering, on the other hand, MIPS are always considered to be very highly specific. So how does that fit? Because you are not going to detect exactly this one bacteria which you mimic in your molecular imprinted polymer, but there's a wide range of changes which a bacteria, there's mutations, there are stems, different stems, whatever. So how could you make a MIPS sensor which covers all these kind of different bacteria if you have such high specific MIPS?
This is a very interesting question. I could talk a lot about this, so please stop me whenever you think it's the case. When we talk about sensitivity and bacteria cells, of course we have a lot of different bacteria that we want to detect. And the reason why this research is so specific is that it uses a specific toxin related to Pseudomonas aeruginosa, in this case the bacterium that I focused on. A way to make these MIPS being selective yet more versatile, so make them able to detect a wider variety of interference, is to ideally find a molecule, so a toxin, a quorum-sensing molecule, anything that is secreted by the bacteria that all the bacteria have in common, and use that as a target, so that instead of detecting one bacterium only, you can detect multiple bacteria. But again, then you have the consequent issue, meaning what is the bacterium that I have in my sample? So eventually you always need a specific sensor to understand what is the bacterium.
But the same is true for the antibiotics, yeah? Usually you are not only wanting to have one antibiotic molecule, but there's a range of antibiotic molecules. How you overcome this with MIPS?
In this case, you can use maybe for same antibiotic classes, like the sulfamethoxazole that belongs to the sulfonamides, have all specific functional groups, like the sulfonamides that can be used maybe to imprint your polymer so that it's able to detect all the antibiotics of that class. A possible alternative, which I didn't investigate, so let me say this first and make it clear, is to make a multi-target molecularly imprinted polymer, meaning that instead of using only one target, only the antibiotic that you want to detect, you use multiple, so a mixture of antibiotics to imprint your polymer. Therefore, this could lead to a sensor that is able to detect a different type of antibiotics. But then you also have maybe the consequent issues related to these, meaning how sensitive is this, how easy is to operate in certain concentration ranges, how easy to scale it up, how miscible are the components among themselves, what are the cross interactions that you might have between the different functional groups of the antibiotics.
You have to be careful,
you have to be careful.
Okay, one last question I would have is, I know it's very important for dairy plants to measure antibiotics in milk, and you mentioned it's because we do not want to uptake antibiotics and want to have multi-resistant bacteria, but there is a much more profound reason they do not want to have antibiotics in milk. Do you know that?
That you don't want to feed the kids with, I don't know.
Why it's really killing dairy plants if you have antibiotics in milk, but why? They are very keen to know. If you are a farmer and you bring milk in which has antibiotics, you really are in trouble, but why?
I have to be honest, I don't know, or at least now I don't have the
Have you
brain
ever
clear
tried
enough.
to create cheese with antibiotic milk? You can't do any yogurt
For
or cheese or whatever.
pasteurization and all the processes.
It will not work. So if you have a
Okay.
farmer who brings in antibiotic contaminated milk, the entire cheese plant will
Yeah, that's
crunch.
actually
So
a very
that
good
is,
point. I didn't know.
the main reason for the milk part, yeah.
Yeah,
Okay,
thank you for mentioning
thanks a lot.
that.
Thanks, yeah.
Thank you.
Thank you, Professor Wagner. Then your position will be continued by Professor Kathleen Diener. She is the Vice President for Research and Innovation at the Hochschule Niederrhein in Germany. Please, Professor Diener.
Thank you, dear candidate. Thank you for the great presentation of a complex topic, but in a very comprehensive way. And so we had like a very detailed talk on the experiments you did and your results. I would like to focus on your next step or potential next step. So you highlighted a very important aspect and a problem you tackle with your solution. Now you made the first step and delivered a proof of concept. So bring it to the market, thinking more into the transfer path. What would you say would be the next step from lab to field in terms for further validation? What would be your choice of setting? What would be your design factors you think you have to further develop to make a robust sensor?
Highly esteemed opponent, thank you very much for this interesting question. I have to say this is one of my favorite topics to talk about because let's say the way you translate a technology into the market is always interesting to tackle, right? Let's say that there are different phases when you want to sell a product. And as I mentioned before, this is the first phase that I took into consideration for my thesis, and it's the feasibility study. So first of all, you have to assess if it's possible with science to reach the goal that you want to reach. So in this case, is it possible to use specific materials to enhance the interaction of certain targets to the actual surface and detect the presence of these contaminants? And the answer that we gave with this thesis is yes. But this is just the first phase, because the second phase of to go to the market is to scale up your product and also to assess the reproducibility and the durability of your product, as I mentioned in the conclusions. So this second step is the ideally step that now needs to follow. So better study the performances of these sensors, understand if it's better to use other materials that are more solid, that gives more selectivity, and ends up in a more solid technology overall. And once that this is addressed, the scalability also arrives. So connected also to the first question that I had, you have to understand how feasible it is to scale up your process, what are the quantities, but before this, you should understand who your customer is, so what is the market, right? Mm-hmm. Once that you do that, you can understand what are the volumes you're working with, where you have to interact with the customers, and also what are the prices that you have to set, and what is the budget? This is, I think, the most important thing in every product development. Once that is done, so once that everything works, feasibility is great, reproducibility is great, you can scale up, you have customers that test your product, and they are happy with your product, you're ready for market launch.
Mm-hmm. Thank you very much. That was a really good description of the transfer path. And here it comes to customer. The customer is usually not an easy person, comes with a lot of personalities. And here my question, what do you anticipate for like a specific customer? Is it the farmer? Is it the food industry? And where do you think you would experience adoption barriers?
Thank you for this question, because I think it's the most sensitive topic probably related to this research, because during my studies, I focused on the detection of the toxin, for instance, in biological samples, and this includes, of course, working in a healthcare setting, in hospitals. In that case, it would be good, of course, to have a sensor that is low cost and that is fast, But I have to say that hospitals are probably the best locations to have also more complex equipments. If you have the equipments that I mentioned before among the gold standard technologies in a lab that is on another floor of your hospital, as it does happen here in Maastricht, by the way, it's for sure easier to detect contaminations in your samples. But if you are talking about more remote location, such as a farm or whatnot, there it's really important to have a portable device. In these cases, the limitations that might be coming are the costs, of course. I'm sorry that I always go back to these, but it's definitely key because no one wants to pay a lot of money to detect and to understand if your sample is contaminated, because if you pay more money than the money that you actually make with your product, then yeah, why are you even working? But this might be one of the limitations for sure, so prices and portability, as I mentioned. But indeed, these are also the more interesting locations where these sensors have to be applied, because in resource-limited settings, it's good to see if your water is contaminated, if your food is contaminated, if you have an infection ongoing. So this is where I would like to see such technologies applied.
Thank you. I don't know. Do I have another question?
Yes, please.
Yeah. Okay. Then I would like to ask, if you look back, reflect your process of finding the dissertation, would you change anything in your experiments now that you're wiser?
Let's say that I'm really happy of how I carried out the research, but of course when you start, you don't know anything about anything, so I'm really also happy that I had the guidance of the people here on my left and also of many people in the audience. Because what I'm really happy about is that I managed to put my hands on different type of technologies, which is really why I'm really happy that I structured my thesis like this. So probably at this point I would say no, I wouldn't change anything.
That was very well timed. Margaux Frigoli, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. And I request that you and your company, the audience, await the results of our deliberations and our return in this room. I adjourn. Margaux Frigoli, the degree committee here present has assessed the quality of your thesis and your defense. And in view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Dr. van Grinsven is authorized to confer upon you this academic distinction in accordance with Dutch university custom, and I invite your supervisor to now take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Margaux Frigoli, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree of certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. Dear Margaux, you made it. You are officially out of this situation.
Yeah.
Now, in true SE tradition, it is upon me to reflect on our 4-year journey. It is time for model letter 10, the speech. And normally, if someone would ask me how often I had to reflect about the past when writing a speech, I would be clueless. But this time, I know exactly. It was 1,020.62 times over the past 6 days. But in those 1,020.62 times, there is a lot that went through my mind. I think it is safe to say that apart from the good times and the successful PhD project, our personalities has clashed a couple of times over the past few years. And we both have very thick skulls. And this has led to several situations that took us a while to solve and to realize that we've always been on the same side. In the end, we both wanted you here on this stage. Luckily, you and I both had brothers in arms to help us realize and see this in tricky situations. You were doing your PhD at the same time as your close friend, Manlio, a friend you loved, respected, and fought with. And whenever we reached boiling point, it was Manlio 100% Caldera, but also Jill and Joe, who were able to place things in perspective so we could come to an agreement and work towards our mutual goal. From my side, I was in the lucky position that I could run the group with my best friend, Casper. And whenever we reached that state of mind again, I could fall back on my friend, who was able to mediate between the both of us. We trusted Casper. He could always make us laugh and make us see that in the end we were exactly on that same side. But then there is life. Manlio defended his PhD on November 23rd, 2023, and he moved on. He was and still is a close friend, but I could feel that you missed him, both in the office and in the lab. And you still had support and friendship in the group, but I could tell you were missing something. And then, 1 year later, disaster struck, and I lost my brother in science. Our Casper got sick. I'm thankful that he's still here, but I think it's safe to say that we miss him every day. And for us, the two of us, this meant that we had to find a way to get to this stage where you are now without our mitigating friends. And I can think we can describe it as a phase where we had to face and fight a lot of hurdles. We had to find a way to align our personalities, timelines, and expectations. But here you are, Dr. Margaux Frigoli. You did an amazing job. You delivered high-quality work. You managed to do so despite some of the conflicts between us, and I'm really proud of how you grew as a scientist. You had a clear vision of your project, designed several highly interesting experiments, and managed to turn them into high-impact publications. You managed to impress us on many occasions, for which I want to congratulate and thank you today. You did an amazing job, and are more than ready for the next stage in your career as a company gal. I think I speak for everyone in the department if I say that we will miss you at SE. In addition to seeing you become an excellent scientist, I also had the pleasure to see you grow as a person. You came in as a fresh university graduate, motivated but also a bit insecure. And now 4 years later, you matured into a woman that knows what she wants, now engaged, supported for this milestone in your life by your partner, your family, your friends and colleagues. I am confident that you will be as successful in the rest of your life as you were in 4 years of SE. My dear Margaux, congratulations and good luck for all your future endeavors. Don't be a stranger, keep in touch, because you will always be an SE member forever. Congratulations.
Thank you so much.
Dear Dr. Frigoli, also on behalf of Maastricht University, I would like to congratulate you with the degree you just obtained and a very nice defense. The committee was really positive on that. Let me also take the opportunity to congratulate the family and friends and everyone here present who are dear to you. And I would like to congratulate the supervisory team for a job well done and a very enjoyable defense that we had here today. Also my thanks to the members of the committee for all the effort you put in and for traveling here, especially those who came from abroad. That's very much appreciated by Maastricht University. So let me close the official part of the session. And then we have a few household announcements.